Hello there, and welcome to Simple Sleepy Science. Right now, as you listen to these words, the ground beneath you is moving. Not dramatically, not violently, but in the slowest, most patient dance imaginable. The earth is alive, constantly shifting, breathing, adjusting itself in ways so subtle that you'll never feel them. And those earthquakes you've heard about? They're not disasters waiting to happen. They're simply the planet's way of staying balanced, like a deep breath after a long day. Before we go further, hit that like button and subscribe so you don't miss more amazing stories tomorrow. Drop a comment telling us where you're watching from and what time it is there. Now, let's discover why earthquakes are actually one of nature's most peaceful processes. We think of earthquakes as sudden, violent events that shake buildings and crack roads. But that's only seeing the final moment of a story that takes decades, centuries, sometimes millions of years to unfold. The truth is far more beautiful and infinitely more commanding than you've ever imagined. Every earthquake is the Earth completing a movement that started long before humans even existed and will continue long after we're gone. The ground you're standing on right now sits on massive plates of rock, each one floating on a layer of partially molten material deep below. These tectonic plates cover the entire planet like pieces of a spherical puzzle, fitting together in ways that determine where mountains rise, where oceans form, and where continents meet. And here's the remarkable part: they're always moving. Always. Every single second of every single day, these enormous slabs of Earth's crust slide past each other, collide, or pull apart. But here's what makes this truly peaceful. These plates move at the same speed your fingernails grow. That's it, about 2 to 4 inches per year. Imagine the patience required for that kind of movement. The plate beneath your feet might travel the length of a football field in an entire human lifetime. This isn't violence. This is geology, moving at the pace of deep time, where 1,000,000 years is just a moment in the Earth's story. Think about what this means. The continents themselves are passengers on these plates, moving across the face of the planet like ships on an impossibly slow ocean. Europe and North America are moving apart right now, creating more Atlantic Ocean between them, but so gradually that it doesn't matter to anyone's daily life. Africa and Europe are slowly colliding, which will eventually close the Mediterranean Sea, but not for millions of years. California is sliding northward along the Pacific Plate, heading toward Alaska, but it won't get there for tens of millions of years. Earthquakes happen when these plates, moving at their glacial pace, encounter resistance. Rock builds up stress over decades or centuries as plates try to move past each other. Finally, that stress releases. The rocks snap into their new position, and the ground shakes for a few seconds or minutes. Then everything settles back into its patient, endless movement. The earthquake isn't a disruption of normal. The earthquake is normal, just sped up into a moment we can actually perceive. These massive plates don't just sit on solid ground, they float. Beneath your feet, miles below the surface, the Earth becomes something entirely different. The rock down there is so hot and under so much pressure that it behaves less like the stone you know, and more like thick honey. Not liquid, but not quite solid either. Scientists call this layer the asthenosphere, which just means the weak sphere. the rock there can flow, incredibly slowly, like cold syrup poured in winter. Picture it this way. You know how ice floats on water? The tectonic plates work the same way. These enormous slabs of cooler, harder rock float on that deeper layer of almost flowing stone. The plates themselves are called the lithosphere, the rock sphere. They're between 50 and 120 miles thick. That sounds massive until you realize the Earth's radius is nearly 4,000 miles. These plates are actually quite thin compared to the whole planet, like sheets of ice on a deep pond. 7 major plates cover most of Earth's surface. The Pacific Plate, the North American Plate, the Eurasian Plate, the African Plate, the Antarctic Plate, the Indo-Australian Plate, and the South American Plate, plus dozens of smaller ones fitting between them. Each one carries continents, ocean floors, or both. They've been moving this way for billions of years, rearranging the face of the planet in a process so slow that mountains rise and fall, oceans open and close, and entire species evolve and go extinct before the plates travel any significant distance. What makes them move? Heat. Deep inside the Earth, radioactive elements decay, releasing energy that warms the planet from within. This heat has to go somewhere. It rises toward the surface in enormous, slow circulation patterns called convection currents. Think of a pot of soup on the stove. The hot soup at the bottom rises. The cooler soup at the top sinks, creating a circular motion. The same thing happens in Earth's mantle, the thick layer between the crust and the core. These currents drag the plates along, inch by inch, year after year. Some plates push together. When they meet, one might slide beneath the other in a process called subduction. The descending plate sinks back into the hot mantle, where it eventually melts and gets recycled. This happens along the edges of the Pacific Plate, creating deep ocean trenches, the deepest places on Earth. The Mariana Trench, nearly 7 miles down, formed this way. Other plates pull apart. As they separate, hot rock from below rises to fill the gap, creating new ocean floor. The Atlantic Ocean grows wider this time every year because the plates on either side are pulling apart along the mid-Atlantic ridge. Then there are plates that slide past each other sideways, grinding along their edges. The San Andreas Fault in California marks where the Pacific Plate slides northwest past the North American Plate. They're not colliding or separating, they're just moving in different directions at different speeds, creating friction as they go. All this happens without any intention or awareness. The plates don't know they're moving. They don't choose their direction. They simply respond to forces built into the planet's structure. Heat rises, cool material sinks, pressure builds, rock bends. Eventually, something has to give, and when it does, we call it an earthquake. But that earthquake is just the plates continuing their ancient journey, adjusting their position by a few feet or inches after years of being stuck together. The continents we know today haven't always been where they are now. Africa wasn't always across the ocean from South America. India wasn't always attached to Asia. Antarctica wasn't always at the South Pole. The map of Earth you see today is just one frame in an incredibly long movie that's been playing for hundreds of millions of years. About 300 million years ago, all the continents were stuck together in one enormous landmass called Pangaea. One supercontinent surrounded by one massive ocean. If you stood in the middle of Pangaea, you'd have to walk thousands of miles in any direction before reaching a coast. The climate there was intense, with scorching deserts in the interior, because ocean breezes couldn't reach that far inland. Dinosaurs would eventually walk across this connected land, their fossils ending up on continents now separated by oceans. Then Pangaea started breaking apart. Not suddenly, not catastrophically, just slowly pulling apart at the seams as the plates beneath it shifted. First, it split into two large pieces. Laurasia in the north, which would become North America, Europe, and Asia. Gondwana in the south, which would become South America, Africa, Antarctica, Australia, and India. The gap between them became the Tethys Sea, an ancient ocean that no longer exists. Over the next 200 million years, those pieces continued fragmenting. South America and Africa separated, creating the Atlantic Ocean between them. If you look at their coastlines on a map, you can still see how they fit together like puzzle pieces. The bulge of Western Africa matches the indent of Eastern South America. That's not coincidence. They were connected, and the rocks on both sides of the Atlantic are the same age and type because they used to be the same piece of land. India broke away from Africa and began one of the most dramatic journeys any continent has ever made. It traveled northeast across the ancient ocean at unusually high speed for a continent, about 6 inches per year instead of the usual 2. About 50 million years ago, India collided with Asia. But it didn't stop. It kept pushing. And because both landmasses were made of light continental rock that doesn't sink into the mantle easily, neither could slide beneath the other. Instead, the collision crumpled the crust between them, pushing it upward. The Himalayas rose from that collision, and they're still rising today as India continues pushing north. Australia separated from Antarctica and began moving north toward the equator. Antarctica, once part of a connected landmass that included South America and Australia, ended up isolated at the South Pole, where it froze under permanent ice. North America and Europe, which had been connected through Greenland, finally separated as the Atlantic widened. This movement never stops. Right now, Africa is pushing into Europe, slowly closing the Mediterranean Sea. In 50 million years, the Mediterranean might be gone, replaced by a new mountain range stretching from Spain to the Middle East. The Atlantic continues widening. The Pacific continues shrinking. California inches toward Alaska. Australia moves north toward Southeast Asia at about the same speed your fingernails grow. In another 250 million years, the continents might merge again into a new supercontinent. Scientists have even given it a name, Pangaea Ultima. The Atlantic might close. The Americas might merge with Africa and Europe. Asia might connect with the Americas across the Arctic. The cycle that broke apart Pangaea would complete, creating a new unified landmass. Then, eventually, that too would break apart, and the dance would continue. When an earthquake happens, the energy doesn't just shake the ground where the plates slip. It travels. The movement sends waves rippling through the entire planet, passing through thousands of miles of rock, crossing oceans, circling the globe. These seismic waves are how we know what's inside the Earth. They're our only way to see into depths we can never reach. There are different types of seismic waves, and each one moves differently through the planet. Primary waves, called P waves, travel the fastest. They compress and expand the rock as they pass through, like sound waves moving through air. These waves can move through solid rock, liquid metal, anything. They arrive first at seismograph stations, giving the initial warning that an earthquake has occurred somewhere in the world. Secondary waves, or S waves, come next. They move the ground side to side, up and down, perpendicular to their direction of travel. Think of shaking a rope to make a wave travel along it. S waves are slower than P waves, and they have one crucial limitation: they can't travel through liquid. This single fact revealed one of Earth's greatest secrets. In 1906, a scientist named Richard Oldham noticed something strange about earthquake recordings. Seismographs on the opposite side of the Earth from a major earthquake showed P waves, but no S waves. The S waves simply vanished. There was a shadow zone where they never arrived. The only explanation was that S waves hit something liquid deep inside the planet and stopped. That's how we discovered Earth has a liquid outer core. We've never been there, never drilled that deep, never directly sampled it. But the waves told us it exists. The waves do more than reveal the core. As they travel through different layers of the Earth, they speed up, slow down, or bend depending on what they're passing through. Dense rock makes them move faster. Less dense rock slows them down. By measuring how long waves take to travel from an earthquake to thousands of seismograph stations around the world, scientists can map the Earth's interior like doctors use ultrasound to see inside a body. This is how we know the Earth has layers. The thin outer crust, broken into those tectonic plates. The thick mantle beneath, made of hot rock that can flow over millions of years. The liquid outer core, made of molten iron and nickel, generating Earth's magnetic field as it swirls around. And at the very center, the solid inner core, a ball of iron crystallized under such extreme pressure that it stays solid, despite temperatures hotter than the surface of the sun. Surface waves travel along the Earth's outer layer, moving more slowly than P waves or S waves, but often causing more damage in earthquakes because they create larger ground movements. They roll through the landscape like ocean waves moving across water. Some make the ground ripple up and down, others make it sway side to side. These are the waves people feel most strongly during earthquakes. Every earthquake, no matter how small, sends these waves through the planet. A minor tremor in Japan creates waves that reach California. A quake in Chile sends vibrations through Antarctica. The Earth rings like a bell after major earthquakes, vibrating at frequencies too low for humans to hear, but detectable by sensitive instruments. These vibrations can continue for days or weeks, the planet slowly settling back to stillness after being struck. The Pacific Ring of Fire sounds like a place of destruction. It's a 25,000-mile arc of volcanoes and earthquake zones encircling the Pacific Ocean, touching the coasts of South America, North America, Japan, the Philippines, Indonesia, and New Zealand. About 90% of the world's earthquakes happen there. 3/4 of the world's active volcanoes line its edges. But calling it destructive misses the real story. The Ring of Fire is where Earth creates itself. The Pacific Plate, the largest tectonic plate on Earth, is surrounded by other plates pushing against it. As these plates converge, the denser oceanic crust of the Pacific Plate slides beneath the lighter continental crust of the surrounding plates. This subduction process drives everything that happens in the Ring of Fire. The descending plate carries water trapped in its rocks down into the hot mantle. That water lowers the melting point of the rock around it, creating magma that rises toward the surface. When that magma reaches the surface, it becomes a volcano. This isn't random violence. It's recycling on a planetary scale. The ocean floor created at mid-ocean ridges eventually gets old, cool, and dense. It sinks back into the Earth along subduction zones, melting and mixing back into the mantle. Millions of years later, that same material might rise again as new crust somewhere else. The Ring of Fire is one part of this cycle, the place where old ocean floor returns to the depths. Japan sits where the Pacific Plate dives beneath the North American and Eurasian plates. The country experiences thousands of earthquakes every year, most too small to feel. The Philippines and Indonesia sit along the boundary where the Pacific Plate meets several smaller plates. The Andes Mountains in South America rose because the Nazca Plate, a piece of ocean floor, pushes beneath the South American plate, crumpling and lifting the continent's edge. These subduction zones create the deepest places on Earth. The Peru-Chile Trench runs along South America's Pacific coast, dropping more than 5 miles below sea level. The Japan Trench plunges even deeper. The Mariana Trench, the deepest point in any ocean, reaches nearly 7 miles down where the Pacific Plate descends beneath the smaller Mariana Plate. At those depths, the pressure is so intense it would crush anything that isn't specifically built to survive there. But these trenches aren't empty graves. They're full of life. Unique ecosystems exist in those depths. Creatures that have never seen sunlight, feeding on chemicals seeping from the Earth's interior. The subduction process releases minerals and nutrients that eventually make their way into ocean currents, feeding ecosystems thousands of miles away. The volcanic islands created by the Ring of Fire become homes for forests, birds, insects, entire communities of life that wouldn't exist without this geological process. New Zealand sits where the Pacific Plate meets the Australian Plate. In some places, the Pacific Plate sinks beneath the Australian. In others, the reverse happens. This creates a landscape of active volcanoes, geothermal areas, and frequent earthquakes. Iceland, though not part of the Ring of Fire, shows what happens when plates pull apart instead of colliding. It sits on the mid-Atlantic ridge, where magma rises to create new land, building the island from below even as ice covers it from above. The Ring of Fire has been shaping coastlines, building mountains, and creating islands for hundreds of millions of years. It will continue long after humans are gone. While major earthquakes make headlines, something quieter happens constantly beneath our feet. Every single day, thousands of earthquakes occur around the world that no human being feels. These micro-earthquakes release energy so gradually and gently that they pass completely unnoticed. They're not failures of the Earth's system. They're the system working perfectly, releasing pressure in tiny amounts instead of letting it build to dangerous levels. Seismologists estimate that several million earthquakes happen worldwide each year. Only about 100,000 of those can be felt by people. The rest are too small, their magnitude so low that only sensitive instruments detect them. A magnitude 2 earthquake releases about as much energy as a hand grenade. You'd have to be standing right above it to notice anything. A magnitude 1 releases even less, comparable to a small construction blast. Below magnitude 1, we're talking about vibrations barely stronger than a truck driving past your house. These tiny quakes happen everywhere. Tectonic plates meet or fault lines exist. California experiences thousands of micro-earthquakes annually along the San Andreas Fault and its countless smaller branches. Most residents never know they're occurring. Japan's sophisticated seismograph network detects thousands more. Even places far from plate boundaries, like the middle of continents, experience occasional microquakes as ancient faults adjust to slow changes in pressure. What makes these small earthquakes fascinating is what they prevent. Every time a fault slips, just a tiny bit, it releases a small amount of stored energy. That's energy that isn't building toward a larger event. Some faults seem to slip smoothly at the microscopic level, constantly releasing pressure in amounts too small to matter. Other faults lock up, their surfaces catching against each other, allowing pressure to build for years or decades until it releases all at once in a noticeable earthquake. Scientists study patterns in micro-earthquakes to understand larger ones. If a fault section that normally produces steady, small quakes suddenly goes quiet, that might mean the fault is locking up, storing energy for a future release. If microquakes increase in frequency in one area, that could indicate stress building to a level where larger movement becomes possible. These patterns aren't perfect predictors, but they provide clues about what's happening deep underground. Oklahoma, traditionally a place with very few earthquakes, began experiencing thousands of small quakes starting around 2009. The cause wasn't natural plate movement, but human activity. Wastewater injection from oil and gas operations added fluid pressure to faults deep underground, making them slip. Most of these induced earthquakes were small, magnitude 3 or below, but they proved that even tiny changes in underground conditions can trigger fault movement. The faults were already there, under stress, waiting for something to tip the balance. Geothermal areas also produce constant micro-earthquakes. Yellowstone National Park, sitting above a massive volcanic hotspot, records thousands of small quakes each year as hot rock shifts and magma moves underground. These aren't signs of an impending eruption. They're normal activity for such a geologically active area, the Earth's crust adjusting to heat and pressure from below. The fact that most earthquakes are unfelt is actually reassuring. It means the Earth isn't storing all its stress for catastrophic releases. Energy flows through the planet constantly, most of it dissipating harmlessly in movements too small to matter. The planet breathes, adjusts, settles, and continues its slow transformation. For most of human history, people had no way to measure earthquakes. They could feel them, describe them, estimate their strength based on damage, but they couldn't record exactly what happened beneath the surface. That changed in 1880 when scientists developed the first true seismograph, an instrument elegant in its simplicity. It worked on a principle so basic that once you understand it, you'll wonder why no one thought of it sooner. The challenge was this: when the ground shakes, everything attached to the ground shakes with it. How do you create something that stays still when everything around it moves? The solution involved inertia, the tendency of objects to resist changes in motion. A seismograph suspends a heavy mass from a frame. When the ground shakes, the frame moves with it, but the heavy mass wants to stay put because of its inertia. The difference between the moving frame and the stationary mass gets recorded, creating a visual trace of the earthquake. Early seismographs used a pen attached to the mass, drawing on paper wrapped around a rotating drum attached to the frame. When the ground stayed still, the pen drew a straight line. When the ground shook, the line became jagged. The size of the jaggedness showed the strength of the shaking. The timing showed how long it lasted. Simple, mechanical, and effective. Modern seismographs work on the same basic principle, but use electronics instead of pens. They convert the motion into electrical signals that computers can analyze instantly. These instruments are so sensitive, they can detect a person walking past the building. They pick up ocean waves crashing on distant shores. They record the rumble of traffic, the movement of trains, even changes in atmospheric pressure. Separating real earthquake signals from this constant background noise requires sophisticated software and careful calibration. A single seismograph can detect that an earthquake happened, but it can't tell you where. For that, you need at least 3 stations. When an earthquake occurs, each station records the arrival time of the P waves and S waves. Because P waves travel faster, they arrive first. The time difference between P wave and S wave arrival tells you how far away the earthquake was. Draw circles around 3 different stations based on those distances, and the point where all 3 circles intersect marks the earthquake's location, its epicenter. Thousands of seismograph stations now monitor the Earth continuously, forming networks that can pinpoint earthquake locations within minutes and determine their magnitude automatically. The United States Geological Survey operates stations across America and territories. Japan's network is even more extensive, with stations in every prefecture. These networks share data globally, so an earthquake anywhere can be detected and analyzed by scientists worldwide almost instantly. Seismographs also revealed that Earth's interior isn't uniform. By tracking how fast seismic waves travel through different parts of the planet, scientists discovered temperature variations, density changes, and compositional differences in the mantle and core. They found that some areas of the mantle are hotter and some cooler, creating the convection currents that drive plate movement. They discovered the boundary between the solid inner core and liquid outer core, and measured both their sizes. Every earthquake, from the smallest tremor to the most powerful ground rupture, gets recorded somewhere. This continuous monitoring creates a growing dataset that helps scientists understand not just individual events, but the patterns and processes that drive them. A fault is simply a crack in the Earth's crust, where rocks on either side have moved relative to each other. They're not failures or weaknesses. They're essential features of how the planet works, the joints and seams that allow solid rock to accommodate movement without shattering completely. Without faults, the pressure from tectonic motion would have nowhere to go. Faults come in three basic types, each responding to different kinds of stress. Normal faults form where the crust is being pulled apart. One block of rock slides down relative to the other, creating a stepped landscape. The Basin and Range Province in Nevada and Utah is full of normal faults, creating the parallel mountain ranges and valleys that give the region its name. The crust there is stretching, thinning, allowing blocks to drop down between the ranges. Reverse faults, also called thrust faults, form where the crust is being compressed. One block of rock gets pushed up and over another. The Himalayas contain massive thrust faults, where India's continuing push into Asia forces rock layers to ride up and over each other, stacking them like cards being shuffled together. These faults create some of Earth's highest mountains by literally piling the crust higher. Strike-slip faults occur where blocks slide past each other horizontally. The San Andreas Fault is the most famous example. The Pacific Plate moves northwest, while the North American Plate moves southeast, and the fault is the boundary where they grind past each other. If you stood on one side and your friend stood on the other, you'd be moving in opposite directions at about 2 inches per year. Over millions of years, that adds up. Rocks that were once side by side now sit hundreds of miles apart. Most faults aren't single clean breaks. They're zones of fractured rock, sometimes miles wide, where the main fault branches into countless smaller fractures. The San Andreas isn't one crack, but a system of parallel and intersecting faults, each capable of producing earthquakes. This complexity makes predicting exactly where and when movement will occur extremely difficult. Faults can be active or inactive. An active fault has moved recently in geological terms, meaning within the last 10,000 years or so, and could move again. An inactive or ancient fault hasn't moved for millions of years, and probably won't move again because the stress that created it no longer exists. The Appalachian Mountains contain many ancient faults from when those mountains were being formed hundreds of millions of years ago. They're locked now, fossils of ancient tectonic forces. Some faults creep continuously, moving so slowly and steadily that they never build up enough stress for noticeable earthquakes. The Hayward Fault in California creeps at about 5 millimeters per year in some sections. You can see this creep breaking curbs, offsetting fence lines, and cracking building foundations over decades. Other sections of the same fault are locked, storing stress that will eventually release in earthquakes. The depth of a fault matters too. Shallow faults within the upper 10 miles of crust produce earthquakes people can feel strongly. Deeper faults produce waves that have to travel farther through rock to reach the surface, which dampens their effect. The deepest earthquakes occur in subduction zones, where one plate descends far beneath another, sometimes releasing energy from depths of 400 miles or more. Every fault tells a story about the forces acting on that part of the crust, recording the history of plate movements in the pattern of broken and shifted rock. Most earthquakes happen within the top 50 miles of Earth's crust, where rocks are cool enough to be brittle and break under stress. But some earthquakes occur at depths that shouldn't be possible. Deep focus earthquakes strike from 200 to 400 miles underground, in conditions so extreme that rock shouldn't fracture at all. At those depths and pressures, rock should flow like putty instead of snapping like a branch. Yet these deep earthquakes happen regularly, and for decades, scientists couldn't explain why. The answer lies in subduction zones, where one tectonic plate descends beneath another. As the oceanic plate sinks into the hot mantle, it carries cool rock into depths where temperatures would normally make rock too soft to break. But the descending plate stays cooler than the surrounding mantle for millions of years because rock conducts heat slowly. This creates a strange situation: cold, brittle rock surrounded by hot, flowing rock. Deep earthquakes follow the shape of these descending plates. Seismologists can map subduction zones by plotting deep earthquake locations. They form slanted planes extending from the ocean floor down into the mantle, marking the path of the sinking plate. The Pacific Plate produces deep earthquakes as it descends beneath Japan, South America, and island arcs throughout the Pacific. Some of these earthquakes occur at depths where the pressure exceeds 130,000 atmospheres, far beyond anything we can recreate in a laboratory. The mechanism that allows rock to fail at these depths remains partially mysterious. One theory involves water trapped in minerals within the descending plate. At extreme pressures, these minerals release their water, causing sudden changes in the rock structure that produce earthquakes. Another theory suggests the rock undergoes phase changes, transforming from one mineral structure to another in a way that generates seismic waves. Both processes might be happening, creating different types of deep earthquakes. What makes deep focus earthquakes remarkable for people on the surface is how harmless they usually are. The energy has to travel hundreds of miles through rock before reaching the surface. By the time the waves arrive, they've spread out and weakened considerably. A magnitude 7 earthquake at 300 miles deep might feel like gentle rolling motion at the surface, barely strong enough to knock objects off shelves. The same magnitude at 10 miles deep would cause severe damage. The deepest earthquakes ever recorded struck around 450 miles deep. Below that depth, even the cold rock of descending plates becomes too warm and soft to fracture. The pressure transforms minerals into denser forms that can flow rather than break. This creates a natural limit on earthquake depth. Nothing deeper than about 450 miles can produce the sudden fracture needed for an earthquake. Deep earthquakes also reveal something profound about Earth's interior. They confirm that plate tectonics operates not just at the surface, but throughout the upper mantle. The plates don't just float on top of the mantle, they sink into it, penetrating hundreds of miles down before finally warming up enough to lose their identity and mix back into the flowing rock. These deep events remind us that Earth's geology operates on multiple levels simultaneously. Surface features like mountains and valleys capture our attention, but equally dramatic processes occur far below. In darkness and pressure we can barely imagine, producing earthquakes that reach the surface as gentle whispers of events unfolding in the deep. In 2001, scientists in the Pacific Northwest noticed something strange on their GPS instruments. Points along the coast of Washington and British Columbia were moving. Not suddenly, not in an earthquake, but slowly over the course of several weeks. The ground shifted about half an inch, then stopped. The movement released as much energy as a magnitude 6.7 earthquake, but nobody felt a thing. They had discovered a slow slip event, an earthquake that takes weeks or months to happen instead of seconds. These silent earthquakes occur along the Cascadia subduction zone, where the Juan de Fuca plate slides beneath North America. Every 14 months or so, deep sections of this fault quietly slip, moving several inches over 2 to 3 weeks. The motion is so gradual that it never generates noticeable shaking. Only sophisticated GPS and seismic monitoring equipment can detect it happening. Slow slip events aren't unique to Cascadia. Japan experiences them regularly along its subduction zones. New Zealand records them. Mexico's coast sees them. Anywhere plates converge, sections of the fault might slip slowly instead of suddenly. These events happen at the transition zone between the locked, shallow part of the fault that produces damaging earthquakes and the deeper sections that slide smoothly all the time. What makes slow slip events fascinating is what they reveal about fault behavior. Not all fault movement has to be violent. Some sections release their stored stress gradually, like letting air out of a balloon slowly instead of popping it. The rock still moves the same distance eventually, but spreading the motion over weeks means the energy gets released without generating strong seismic waves. During slow slip events, the number of small earthquakes often increases in the surrounding area. The gradual movement seems to stress nearby sections of the fault, triggering tiny tremors and quakes. Scientists monitor these patterns carefully because slow slip events might affect when and where larger earthquakes occur. If a slow slip transfers stress to a locked section of fault, it could bring that section closer to failure. The mechanics of slow slip remain somewhat mysterious. The fault surfaces in these zones might be coated with clay-rich materials that allow smooth sliding instead of stick-slip behavior. Water pressure in the rocks might reduce friction enough to permit gradual movement. The exact conditions that allow one section of fault to slip slowly while another section locks up and releases suddenly aren't completely understood. Some slow slip events last just days. Others continue for more than a year. The Hikurangi subduction zone beneath New Zealand's North Island produces slow slip events that last 12 to 18 months, with the fault creeping steadily the entire time. The longer the event lasts, the more total movement occurs, releasing more energy overall, but spreading it so thin in time that it never becomes dangerous. These silent earthquakes show that Earth's crust has more ways to move than we once thought. The old model of faults being either locked or sliding doesn't capture the full complexity. Some sections creep continuously, some slip slowly for weeks, some lock for centuries and then break catastrophically, and some do all three at different times, responding to changing conditions deep underground in ways we're still learning to understand. The discovery of slow slip events changed how scientists think about earthquake hazards. Energy release isn't always dramatic. Sometimes the Earth adjusts itself so gently that only our most sensitive instruments notice. scientists cannot predict earthquakes with the precision most people want. They can't tell you that a magnitude 6 quake will strike a specific city next Tuesday at 3:47 p.m. But they can read the Earth's subtle hints, patterns that suggest where and roughly when earthquakes become more likely. This isn't fortune-telling. It's patient observation of a planet that constantly signals its intentions if you know what to look for. Groundwater levels sometimes change before earthquakes. Wells that have flowed steadily for years suddenly run dry or overflow. Water trapped in rock responds to stress changes in the crust. As pressure builds along a fault, it can squeeze or stretch the surrounding rock, forcing water to move. Scientists in China have documented cases where well levels dropped significantly days or weeks before major earthquakes. But this signal isn't reliable. Many earthquakes show no groundwater changes at all, and groundwater shifts for many reasons unrelated to earthquakes. Radon gas emissions from the ground also fluctuate. Radon forms naturally from radioactive decay in rock. Normally, it seeps up through soil at a steady rate. But changes in underground stress can open or close tiny fractures, altering how easily the gas escapes. Some studies show radon spikes before earthquakes. Others find no correlation. The signal exists, but remains too inconsistent to use as a prediction tool. Animals might sense earthquakes before humans do, though the evidence is mostly anecdotal. Stories of dogs barking frantically, birds abandoning trees, and fish jumping from water hours before quakes appear throughout history across many cultures. The mechanism would be straightforward if true. Animals have different sensory capabilities than humans. They might detect subtle ground vibrations, electromagnetic changes, or even ultrasonic sounds that we miss completely. But controlled studies have found no reliable pattern. For every story of animals predicting an earthquake, there are countless instances where they showed no unusual behavior before major quakes. The most reliable prediction methods focus on probabilities rather than specific events. Scientists know that major earthquakes reduce stress on one section of fault, but often increase it on adjacent sections. After a magnitude 7 earthquake, they can calculate which nearby fault segments now face higher stress and estimate the increased likelihood of earthquakes there. These forecasts work in general terms. They can say a particular fault segment has a 60% chance of a major earthquake in the next 30 years, which helps communities prepare but doesn't enable evacuation warnings. Foreshocks sometimes precede larger earthquakes. A cluster of small quakes in an area that's usually quiet might indicate a larger event building. But most earthquake swarms don't lead to major quakes, and many major quakes strike without any foreshocks at all. The 2011 Tohoku earthquake in Japan had a magnitude 7.3 foreshock 2 days earlier, which seems like an obvious warning in hindsight. But magnitude 7. Earthquakes happen regularly in Japan without being followed by anything larger. Geodetic measurements using GPS can show where strain is accumulating. If two sides of a fault are locked together while the plates try to move past each other, the surrounding crust bends and deforms. GPS stations detect this bending as the ground gradually shifts position. Areas building strain are areas where future earthquakes will release it. But this only tells you where, not when. The fault might rupture tomorrow or in 200 years. The reality is that earthquake prediction remains largely beyond our capabilities. We understand the forces involved. We can identify dangerous faults. But the exact moment when accumulated stress will overcome friction and cause rock to slip remains unpredictable. The Moon has earthquakes too, or more precisely, moonquakes. Between 1969 and 1977, Apollo astronauts placed seismometers on the lunar surface that recorded thousands of tremors originating deep inside our closest celestial neighbor. The Moon, that cold, seemingly dead rock in the sky, shakes just like Earth does. But the causes are completely different. Earth's earthquakes come from plate tectonics, the constant motion of crustal slabs driven by heat from the planet's interior. The Moon has no plate tectonics. It's too small, too cold, and cooled down too quickly after forming to maintain the internal heat needed to drive plate movement. Its crust is a solid shell surrounding a partially molten core with no moving pieces to generate the stress that causes earthquakes. Yet moonquakes still happen. Deep moonquakes occur about 600 to 800 miles below the surface, much deeper than any earthquake on Earth. They happen on a monthly cycle, which provides the first clue to their cause. These deep tremors peak when the Moon is at perigee, its closest approach to Earth each orbit, and at apogee, its farthest point. The changing distance creates varying tidal forces, pulling and squeezing the Moon's interior in a rhythm that matches its orbit around Earth. The stress from these tidal forces triggers moonquakes in the deep interior, where some rock remains slightly warm and capable of fracturing. Shallow moonquakes are different. They're stronger and less frequent, occurring within the Moon's crust rather than deep inside. These might result from the Moon's gradual cooling and shrinking. As the interior loses heat over billions of years, it contracts, causing the outer crust to wrinkle and crack like the skin of a drying apple. These shallow quakes can register magnitude 5 or higher, which would cause moderate damage on Earth. But on the airless Moon, there's nothing to damage. Thermal moonquakes happen when sunlight hits the lunar surface after 2 weeks of frigid darkness. The temperature swing is extreme, from around negative 280 degrees Fahrenheit in shadow to positive 260 in sunlight. Rock expands and contracts with these temperature changes, producing countless tiny tremors as the surface adjusts. These are the most frequent moonquakes, but also the weakest, barely detectable even by sensitive instruments. The fourth type of moonquake is man-made. When Apollo missions crashed their spent lunar modules into the Moon's surface for science experiments, the impacts generated seismic waves that the seismometers recorded. These controlled impacts revealed something strange. The Moon rang like a bell. The vibrations continued for more than an hour after impact, far longer than similar vibrations would last on Earth. This happens because the Moon's interior is dry and rigid. On Earth, water in rocks and soft sediment layers dampen vibrations quickly. The Moon has no water and fewer soft layers, so seismic waves bounce around inside it for much longer. The Moon's seismic activity is far weaker than Earth's. The total energy released by all moonquakes in a year equals roughly 1 magnitude 5 earthquake on Earth. But studying moonquakes taught scientists how to interpret seismic data from bodies that don't have plate tectonics. The same techniques now help us analyze seismic data from Mars, where rovers have detected Marsquakes, and might eventually help us understand the interiors of distant moons in the outer solar system. Every solid body in the solar system probably experiences some form of seismic activity, driven by different forces but following the same basic physics. Rock remembers. Every earthquake that ever shook the planet left traces in the geological record, markers that persist for millions of years if you know how to read them. These aren't written records or human accounts. They're physical disruptions in layers of sediment and stone that tell stories of ancient tremors from times when no witnesses existed to feel them. When an earthquake strikes, it can liquefy water-saturated sediment, causing sand and mud to behave like liquid. This liquefied material sometimes erupts through overlying layers, creating sand blows or sand volcanoes at the surface. When these features solidify, they preserve the earthquake's signature. Geologists digging through sediment layers can find these intrusions, dated by their position relative to other layers, revealing when earthquakes struck thousands of years ago. Turbidites provide another record. These are underwater landslides triggered by earthquake shaking. When strong ground motion shakes the continental shelf, sediment loses its grip and slides down into deeper water, creating a distinctive layered deposit. Each turbidite represents a single event, a rush of sediment settling out of suspension with coarse material at the bottom and fine material at the top. Finding multiple turbidite layers in ocean floor cores shows a pattern of repeated earthquakes over millennia. Fault scarps, where the ground surface breaks along a fault line, persist in the landscape for thousands of years. Each time the fault moves, it creates or enlarges these step-like features. By digging trenches across fault scarps and examining the displaced soil layers, scientists can count past earthquakes and estimate when they occurred. Charcoal from ancient fires or organic material in the soil provides material for radiocarbon dating, pinning down the age of each event. The Dead Sea, transform fault running through the Middle East, has left geological evidence of earthquakes stretching back over 100,000 years. Sediment cores from the Dead Sea itself show disturbed layers marking ancient quakes. These correlate with archaeological evidence of destroyed cities, confirming that earthquakes have struck this region repeatedly throughout human history and long before. The New Madrid seismic zone in the central United States produced 3 massive earthquakes in 1811 and 1812, strong enough to ring church bells in Boston and temporarily reverse the flow of the Mississippi River. But geological studies show this wasn't unusual. The zone has produced similar sequences of major earthquakes roughly every 500 years for at least the past 4,000 years. Liquefaction features buried in Mississippi River Valley sediments mark each event, showing that this seemingly quiet region has a violent geological past. The Cascadia subduction zone off the Pacific Northwest coast last ruptured in a magnitude 9 earthquake in January 1700. We know the exact date because the resulting tsunami reached Japan, where written records noted unusual waves arriving without any local earthquake. But geological evidence shows Cascadia has ruptured about 40 times in the past 10,000 years, roughly every 200 to 500 years. Each rupture lifted or dropped coastal areas, killing forests that then got buried by sediment. These ghost forests, trees still standing in tidal zones where they died, mark the earthquakes. Even rocks deformed under intense pressure deep underground preserve earthquake evidence. Pseudotaculite, a glassy material formed when rock melts during rapid fault movement, represents fossilized earthquake friction. Finding these ancient melt zones in exposed fault rocks shows where earthquakes occurred millions of years ago, revealing the planet's seismic history written in stone. Rock bends before it breaks. This simple fact explains why earthquakes happen and why they take so long to build up. When forces push on rock slowly enough, it doesn't shatter immediately. It flexes like a spring being compressed, storing energy in its deformed shape. This process, called elastic strain, can continue for decades or centuries before the rock finally reaches its breaking point. Harry Fielding Reid figured this out after the 1906 San Francisco earthquake. He surveyed the land on both sides of the San Andreas Fault and compared his measurements to surveys done years earlier. The ground had been gradually shifting. Roads and fences that once ran straight now bent near the fault. But the fault itself had been locked, unable to slip. The bending continued until the rock couldn't hold anymore. Then it snapped, the two sides lurching past each other by up to 20 feet in some places. The bent rock straightened instantly, releasing all that stored energy as seismic waves. Reid called this elastic rebound. Picture holding a stick with both hands and slowly bending it. At first, nothing happens. As you apply more pressure, the stick curves. It's storing the energy you're putting into it. Keep bending, and eventually the stick reaches its limit. It snaps suddenly, the two pieces springing back toward their original shape. That's elastic rebound on a small scale. Faults do the same thing over much longer time periods. The elastic part is crucial. If rock was purely brittle, it would break as soon as any stress exceeded its strength. If it was purely plastic, it would deform slowly without storing energy. But crustal rock in the earthquake-generating zone, roughly the upper 10 to 15 miles, behaves elastically. It can bend and store tremendous amounts of energy before failing suddenly. The San Andreas Fault demonstrates this clearly. GPS measurements show that land west of the fault moves northwest relative to land on the east at about 2 inches per year on average. But the fault itself, the actual contact between the two plates, doesn't move that fast. It's stuck. The rock around it bends instead, like twisting a towel from opposite ends while holding the middle still. Eventually, the stuck section breaks free, and all that accumulated movement happens at once. The longer the time between earthquakes on a fault, the more energy it stores. This is why some faults produce frequent small earthquakes, while others generate rare massive ones. Faults that slip easily don't build up much stress before releasing it. Faults that lock strongly can store energy for centuries, leading to much larger earthquakes when they finally rupture. The trade-off is predictable: frequent small releases or infrequent large ones. The depth where earthquakes can occur is limited by this elastic property. Below about 15 miles, the rock becomes too hot and soft. Instead of bending elastically and then breaking, it flows slowly like taffy, constantly deforming without building up stress. This ductile behavior prevents earthquakes. The boundary between the brittle zone above and the ductile zone below marks the depth limit for most seismic activity. After a major earthquake, the cycle begins again immediately. The fault hasn't disappeared. The tectonic forces haven't stopped. The plates continue trying to move past each other. The rock starts bending again, storing energy for the next earthquake, which might happen in 50 years or 500 years, depending on how fast stress accumulates and how strongly the fault locks. The process is patient, inevitable, and completely natural. When an earthquake ruptures the ocean floor, it doesn't just shake the ground, it moves it vertically, lifting or dropping sections of seafloor by several feet or even tens of feet. This sudden displacement pushes the entire water column above it, creating a wave that spreads outward in all directions. That wave is a tsunami, and it behaves completely differently from ordinary ocean waves. Normal waves are created by wind. They only affect the surface layer of water. A wave that looks 6 feet tall actually only moves the top 6 feet of water. Everything below stays relatively still. This is why a ship in deep water barely notices even large storm waves. But a tsunami involves the entire depth of ocean, from surface to seafloor. When an earthquake moves the bottom, it sets trillions of tons of water in motion all at once. In deep ocean, tsunamis are nearly invisible. The wave might be only a foot or two tall, spread across hundreds of miles of ocean. A ship passing over it wouldn't even notice. But that wave is moving fast as a jet airplane, sometimes reaching 500 miles per hour. The speed depends on water depth. The deeper the water, the faster the wave travels. This creates a strange situation where different parts of the same tsunami travel at different speeds. As the tsunami approaches shallow water near a coast, physics forces it to change. The front of the wave slows down as it drags on the shallowing seafloor, but the water behind it is still moving fast. The wave compresses, like cars bunching up in slowing traffic. As it compresses, it has nowhere to go but up. The wave height increases dramatically. A 2-foot wave in deep water might become 30 or 40 feet tall when it hits the coast. The 2004 Indian Ocean tsunami demonstrated this process with devastating clarity. A magnitude 9.1 earthquake off the coast of Sumatra displaced the seafloor over an area roughly 800 miles long. The sudden uplift created a tsunami that radiated across the entire Indian Ocean. In deep water, boats reported unusual currents, but no obvious wave. Yet, when those same waves reached coastlines throughout the region, they arrived as walls of water exceeding 100 feet in some locations. Tsunamis aren't single waves. The initial earthquake displacement creates a series of waves, each following behind the previous one. Sometimes the first wave isn't even the largest. The 2011 Japan tsunami had multiple waves arriving over several hours, each one flooding areas that survivors of earlier waves thought were safe. The period between waves, the time from one crest to the next, can be 10 minutes to 2 hours, depending on the earthquake's characteristics. The wavelength of tsunamis, the distance from one crest to the next, can exceed 100 miles. This is why they carry so much energy. Even though they might only be a few feet tall in deep water, that small height is maintained across enormous distances, representing a massive volume of moving water. When all that water funnels into shallow coastal areas, the energy has to go somewhere. Not all underwater earthquakes create tsunamis. The seafloor has to move vertically, not just horizontally. A strike-slip earthquake, where two plates slide past each other sideways, generates little to no tsunami, even if it's very strong. But thrust earthquakes in subduction zones, where one plate rides up over another, lift the seafloor and create ideal conditions for tsunami generation. This is why the Pacific Ring of Fire produces most of the world's major tsunamis. You can't stop earthquakes, but you can build structures that dance with them instead of fighting them. This shift in thinking, from rigid resistance to flexible response, has saved countless lives in earthquake-prone regions. The key is understanding that buildings don't fail because the ground moves. They fail because they can't adapt to that movement. Traditional masonry buildings, made of brick or stone stacked with mortar, are particularly vulnerable. These materials are strong under compression, excellent at supporting weight from above, but they're brittle under sideways forces. When earthquake waves shake a building horizontally, the walls crack and crumble. Ancient buildings survived for centuries under their own weight, but collapsed in minutes during earthquakes. Modern earthquake-resistant design uses several strategies working together. Base isolation separates the building from the ground, using special bearings that allow the foundation to move independently from the structure above. Picture a book sitting on a table. If you shake the table, the book shakes too. But if you put the book on several smooth marbles, you can shake the table and the book barely moves. Base isolators work the same way, using layers of rubber and steel that absorb ground motion before it reaches the building. Damping systems absorb energy from earthquake waves, converting the motion into heat that dissipates harmlessly. Some buildings use viscous dampers, like giant shock absorbers filled with thick fluid. As the building sways, pistons push through this fluid, creating resistance that slows the motion. Other designs use friction dampers, metal plates that slide against each other, turning motion into heat through friction. These systems don't prevent the building from moving. They control how much and how fast it moves. Flexible frame design allows buildings to sway without breaking. Steel and reinforced concrete frames can bend significantly without failing. The structure absorbs earthquake energy by deforming temporarily, then springs back to its original shape. Engineers design these frames with ductile connections, joints that can stretch and bend rather than snap. The building might sway several feet at the top during a strong earthquake, which looks terrifying, but is actually the design working correctly. Traditional Japanese architecture understood this principle centuries ago. Wooden temples and pagodas use interlocking joints without nails or screws. When earthquake waves shake the structure, these joints shift slightly, allowing the building to flex. The 5-story pagoda at Horyuji Temple, built in 607 AD, has survived numerous earthquakes using this design. Modern skyscrapers apply the same principle with different materials. Shear walls, strong vertical walls distributed throughout a building, resist sideways motion. They're made of reinforced concrete, with steel bars forming a dense grid inside. These walls don't prevent swaying, but they limit how far the building can move. Combined with flexible frames, they create structures that bend without breaking and return to their original position after shaking stops. The goal isn't to create earthquake-proof buildings. That's impossible and unnecessary. The goal is earthquake-resistant buildings that protect lives. A building might suffer damage, cracks in walls or broken windows, but it shouldn't collapse. People inside have time to evacuate or shelter safely. The structure might need repairs afterward, but it doesn't become a death trap. Even simple improvements matter. Bolting houses to their foundations prevents them from sliding off during shaking. Bracing water heaters and securing heavy furniture stops them from becoming projectiles. These measures don't require sophisticated engineering, just understanding that earthquake safety means accommodating movement rather than trying to prevent it. After every major earthquake comes a sequence of smaller ones. These aftershocks aren't separate events. They're the fault continuing to adjust, settling into its new position after the main rupture. The pattern they follow is so predictable that seismologists can forecast how many will occur and roughly how large they'll be, even if they can't predict exactly when each one will strike. The largest aftershock is typically about 1 magnitude unit smaller than the main shock. If the main earthquake was magnitude 7, expect the largest aftershock around magnitude 6. That's still strong enough to damage buildings already weakened by the initial event, which is why aftershocks are dangerous, despite being smaller. A structure that survived the main earthquake might not survive repeated shaking from aftershocks. Aftershocks decrease in frequency following a mathematical pattern called Omori's Law, discovered in 1894 by Japanese seismologist Fusakichi Omori. The rate of aftershocks drops roughly in proportion to the inverse of time since the main shock. If 100 aftershocks happen in the first day, expect about 50 in the second day, 33 in the third day, and so on. The pattern isn't exact, but it's remarkably consistent across different earthquakes worldwide. Some aftershock sequences last for years. The 1906 San Francisco earthquake generated detectable aftershocks for more than a decade. More recent major earthquakes follow the same pattern. The fault doesn't settle immediately into its new configuration. It continues making small adjustments, releasing residual stress in chunks, each adjustment producing another aftershock. The aftershocks don't occur randomly along the fault. They cluster around the edges of the main rupture zone, particularly at the ends where the rupture stopped. Think of it this way: the main earthquake relieved stress along one section of fault, but that transferred additional stress to the sections immediately adjacent. Those stressed sections respond by breaking in smaller events, which may transfer stress further out, creating a cascade of increasingly smaller earthquakes spreading away from the initial rupture. Sometimes an aftershock can be larger than the main shock, though this is rare. When it happens, scientists reclassify the events. The larger earthquake becomes the main shock, and the original main shock gets demoted to foreshock status. The 2016 Kumamoto earthquakes in Japan demonstrated this. A magnitude 6.2 struck first, followed 2 days later by a magnitude 7.0 on a different fault segment nearby. The initial earthquake apparently triggered the larger one by transferring stress to an adjacent fault. The psychological impact of aftershocks can be as significant as their physical effects. After surviving a major earthquake, people remain on edge, jumping at every tremor. And there will be many tremors. A magnitude 7 earthquake might generate 10,000 aftershocks, large enough to be felt over the following year. Most are minor, barely noticeable, but living through constant ground motion, never knowing if the next shake will be small or significant, creates lasting anxiety. Aftershock zones also reveal fault complexity. By plotting thousands of aftershocks, seismologists can map the three-dimensional shape of the fault surface that ruptured, seeing details invisible in the main earthquake alone. These maps show that faults aren't smooth planes, but rough, irregular surfaces with bends, steps, and branches. Each aftershock illuminates another small piece of that hidden structure. Eventually, the aftershocks fade to background levels, becoming indistinguishable from the normal seismicity of the region. The fault enters a quiet period, slowly accumulating stress again for the next major earthquake, decades or centuries in the future. Volcanoes and earthquakes are connected in ways that run deeper than sharing space along plate boundaries. Volcanic tremor, a continuous low-frequency vibration that can last for hours or days, happens when magma moves underground. Unlike the sudden snap of tectonic earthquakes, volcanic tremor is sustained and rhythmic, like the earth humming as molten rock pushes through cracks in the crust. Magma is less dense than solid rock, so it rises naturally toward the surface, like oil floating on water. As it ascends, it has to force its way through layers of cooler, solid rock. This movement creates pressure waves that seismographs record as harmonic tremor, a signal completely different from regular earthquakes. Where tectonic earthquakes show sharp spikes in seismic data, volcanic tremor appears as continuous wavy lines, sometimes persisting for weeks before an eruption. The tremor's frequency and intensity reveal what's happening underground. High-frequency tremor often indicates magma interacting with groundwater, creating steam that pushes through rock fractures. Low-frequency tremor suggests slow magma movement through larger chambers and conduits. By analyzing these signals, volcanologists can track magma as it rises, estimating its depth and sometimes predicting when it might reach the surface. Mount St. Helens demonstrated this clearly before its 1980 eruption. For weeks, the volcano produced swarms of small earthquakes and continuous tremor as magma pushed into the mountain. The north flank bulged outward, expanding several feet per day as magma accumulated beneath it. When the eruption finally occurred, it released all that built-up pressure in one catastrophic event. But the warning signs were there in the seismic record, written in those weeks of tremor. Hawaii's volcanoes produce different patterns. Because Hawaiian magma is relatively fluid and erupts less explosively than the thick, gas-rich magma at Mount St. Helens, the tremor signals are steadier and less alarming. During active eruptions, Kilauea volcano generates constant tremor as lava flows through underground tubes from summit to coast. This tremor is so persistent that seismographs at the Hawaiian Volcano Observatory record it continuously for months or years during active phases. Iceland sits on a spreading plate boundary where the North American and Eurasian plates pull apart. This creates both regular tectonic earthquakes from plate movement and volcanic tremor from magma rising to fill the gaps. The 2021 Fagradalsfjall eruption was preceded by weeks of intense earthquake swarms, more than 50,000 small quakes as magma forced its way up through 20 miles of crust. The seismic activity migrated gradually toward the surface, mapping the magma's path like a slow-motion X-ray. Submarine volcanoes produce tremor too, though it's harder to detect through ocean water. The 2022 Hunga Tonga eruption, one of the most powerful volcanic events in decades, generated seismic signals that traveled around the world multiple times. The explosion was so violent, it created pressure waves in the atmosphere that circled the planet, detected by barometers everywhere. Not all volcanic tremor leads to eruptions. Sometimes magma rises partway to the surface and then stalls, cooling and solidifying underground. The tremor fades as the magma stops moving. These failed eruptions are common, outnumbering successful eruptions by a large margin. But each event leaves behind a record in the seismic data, and sometimes adds a bit more magma to underground chambers that might feed future eruptions. The connection between earthquakes and volcanoes extends beyond tremor. Large tectonic earthquakes can trigger volcanic activity by changing pressure in magma chambers or opening pathways for magma to rise. Every earthquake that shakes the surface sends waves racing through the entire planet. These waves don't just travel through rock, they reveal it, exposing details about Earth's interior that would otherwise remain completely hidden. We've never drilled deeper than about 7 miles into the crust. The center of the Earth sits nearly 4,000 miles down, unreachable by any technology we possess. Yet we know it's there, know its size, know it's made of iron, know it's partly liquid and partly solid. Seismic waves told us everything. The crust, where we live, is surprisingly thin. Under continents, it averages about 20 to 30 miles thick. Under oceans, only 3 to 5 miles. This is the brittle outer shell, cool enough that its rocks fracture instead of flow. All the earthquakes we feel happen here, in this relatively thin layer sitting atop something much larger. Below the crust lies the mantle, extending down to 1,800 miles deep. This enormous layer contains most of Earth's volume and mass. The rock here isn't molten, but it's hot enough and under enough pressure that it can flow over geological time, like extremely thick honey. Seismic waves travel through it at speeds that vary with depth and temperature, revealing that the mantle has its own internal structure with distinct layers of different mineral compositions. The upper mantle, from the base of the crust down to about 400 miles, is where plate tectonics operates. This is the zone of convection currents that drive the plates above. Seismic waves show that descending tectonic plates can penetrate through this layer, sinking like cold drips into the deeper mantle. The waves also reveal hot plumes rising from below, feeding volcanic hotspots like Hawaii and Yellowstone. Around 400 miles down, seismic wave speeds increase suddenly. This marks a transition zone where pressure transforms the minerals in the mantle into denser crystal structures. The same rock exists above and below this boundary, but arranged differently at the atomic level. Another transition occurs at 410 miles depth, and another at 660 miles. These boundaries show up clearly in seismic data as sharp jumps in wave velocity. The lower mantle extends from 660 miles down to 1,800 miles. Seismic tomography, which works like a medical CT scan but uses earthquake waves instead of X-rays, creates three-dimensional maps of this region. These maps show cold slabs of ancient oceanic crust that have sunk all the way to the bottom of the mantle, accumulating in massive piles near the core mantle boundary. They also show hot regions where material rises from deep within the mantle toward the surface. At 1,800 miles depth, the mantle ends and the outer core begins. Here, seismic waves change behavior dramatically. S waves disappear completely because they can't travel through liquid. This revealed that the outer core must be molten. P waves continue through, but slow down significantly. The composition must be different from the mantle, something denser. The outer core is iron mixed with some lighter elements, kept liquid by temperatures exceeding 7,000 degrees Fahrenheit. Inside the liquid outer core sits the inner core, a solid sphere about 750 miles in radius. Despite being even hotter than the outer core, the extreme pressure at Earth's center squeezes the iron into a solid state. Seismic waves traveling through the inner core move faster when traveling north-south than east-west, suggesting the iron crystals are aligned in a particular direction. All of this knowledge came from earthquakes, from waves that scientists patiently tracked and analyzed over more than a century of careful observation. The Earth beneath you has never stopped moving, not for a single moment in the 4.5 billion years since the planet formed. The continents you walk on are passengers on plates that have traveled thousands of miles, carrying life across oceans that opened and closed, while mountains rose and wore away. Every earthquake is just one small adjustment in this endless transformation, a brief moment when the planet's patient geological processes become fast enough for humans to notice. We tend to think of solid ground as permanent, unchanging, safe, but that's only true at the time scale of human lives. Zoom out to geological time and everything becomes fluid. Oceans appear and vanish. Continents merge and split. Mountains thrust upward and then erode to plains. Earthquakes aren't interruptions to this process. They are the process, just sped up into seconds instead of centuries. Living on a tectonically active planet means accepting that the ground will shake sometimes. There's no way around it. As long as the Earth's interior stays hot enough to drive convection, the plates will keep moving. As long as the plates move, stress will build along their boundaries. As long as stress builds, it will eventually release. This cycle has no endpoint, no moment when the Earth will finally settle down and stop shaking. But this same process gave us the world we inhabit. Plate tectonics created the continents, lifting land above sea level. It formed the mountain ranges that generate weather patterns and create diverse climates. It recycled nutrients from the deep earth back to the surface, enriching the soil that grows our food. It created the varied landscapes, coastlines, and geological features that make Earth such a dynamic home for life. The same earthquakes we sometimes fear are part of the machinery that makes this planet habitable. the slow slip events releasing energy over weeks. The micro-earthquakes, adjusting stress one tiny increment at a time. The deep focus tremors far below where they can cause any harm. The volcanic systems building new land while recycling old oceanic crust. All of it works together in a system that has kept Earth geologically alive for billions of years. Understanding earthquakes changes how we relate to them. They're not punishments or random acts of destruction. They're natural consequences of living on a planet with a hot interior and moving plates. When you know this, the fear diminishes just a bit. Not the respect, the preparation remains essential. But the existential dread of unpredictable chaos gives way to a different feeling. Appreciation for being alive on a world dynamic enough to reshape itself, patient enough to do it over billions of years, and just active enough that we occasionally get to witness the process happening. The next time you feel the ground move, even slightly, remember what you're experiencing. Plates that have traveled across oceans, rock that has bent for decades, finally snapping into a new position, waves rippling through thousands of miles of the planet's interior, ancient processes that have shaped continents and built mountains, compressed into a few seconds of shaking that connects you directly to the geological forces that made this world. If you found peace in these earthquake facts tonight, hit that like button and subscribe for more calming science stories tomorrow. We'll keep exploring the beautiful mechanics of our universe together. Let us know in the comments where you're listening from and what time it is there. Until next time, sleep well, knowing you live on a planet that's constantly, patiently, peacefully reshaping itself beneath your feet.